So in this video, we'll be looking into a couple of formulas that we'll be using in our upcoming lessons. But before that, we'll have to understand the concept of cardinality. Well, cardinality tells about the number of elements in a given set. For example, if you take set A has the elements 1, 5 and 7. So totally, set A has 3 numbers in it. So n of A, and this is how you write it. You put a simple n followed by a curled bracket. Within the curled bracket, you write the name of the set. So NA equals 3. And now what this means is, this just simply says number of elements in A. So the number of elements in set A equals 3. In the second example, set B has 1, 2, 3, 4, 5, 6, 7 numbers. So we say number of elements in set B is 7. In set C, we still have one element. The element is 0, but still the set has an element inside it. So NC is equal to 1. One thing we have to note here is that the cardinality of a set becomes 0 only when the set is an empty set, or also called as a null set. For example, if I say there's a set D and the set D is just this. So you open a curly bracket, close a curly bracket, and you don't have any element inside it. So this is called an empty set or null set. And the cardinality of this set, so number of elements in D, this is equal to 0 because there is no elements inside this set. Okay, so moving on. Now that we understand the idea of cardinality, what are the two formulas that we need to know? So these are the two formulas that we need to remember, and we will be using these formulas in our future lessons. Now let us analyze what these formulas tell us. Let's start with the first formula. The first formula simply says that number of elements belonging to a union set is equal to the sum of the number of elements in the individual set take away the number of elements in the intersection set. Let's see what this means. Let's just go ahead and see a quick example here. So if I say that this is set A and this is set B, and let's say that this set A has, let's say, 1, 2, 3, 4, 5, 6, 7, 8. Now we know set A has 4 numbers, 1, 2, 3, 4. So NA is 4. We don't need to write the set since we can see it by ourselves. And set B has 4, 5, 6, 7, 8. So we have 4, 5, 6, 7, 8. So we basically have 5 numbers there. So NB equals 5. And NA union B is simply the total number of elements that belong to both A and B together. So if you see here, it has 1, 2, 3, 4, 5, 6, 7, 8. So basically 8 numbers that belongs to both the circle. So NA union B is 8. And obviously A intersection B, as you can see, only has one element, which is the number 4. So in A intersection B has just one element. Remember one thing, when we write cardinality, we don't write in terms of curly brackets. So we don't say NA is this. We don't do that. We write curly brackets only when we describe the set itself. This is not the set itself. We are just telling how many elements are there inside the set. So for this, we don't use a curly bracket. So do not mix it up here. When we talk about cardinality, we don't use curly brackets. Alright, so now we know all the 4 numbers. Now just let's verify if the formula is true in this case. So if we just try to plug in the values, NA union B is 8, NA is 4, NB is 5, and NA intersection B is 1. So 4 plus 5 is 9 minus 1 is 8. So this formula works, and this should not be a surprise because you can intuitively understand why it works the way it works. If you go ahead and think about it, remember in a set we do not repeat any numbers, right? So when we have A as, in this case, is 1, 2, 3, 4, and we have B in this case as 4, 5, 6, 7, 8, and A union B is basically 1, 2, 3, 4, 5, 6, 7, 8. So if you have a look at here, we write 4 only once, though there are 2 4s in the sets. When you put together, A has a 4 and B also has a 4, we only write 4 once because we know the rule in a set is that you can't repeat the same element twice within a set. So for that reason, we do not count it. So since we do not count the second 4 as a part of the union set, that 4 is left out. So we have one number that we haven't written, and that one number is our intersection set. Because the intersection set is the set that includes all the common numbers. And if there are common numbers, we will not write it twice. So I believe now you understand why formula works. Now that we've understood how the first formula works, let's go ahead and understand the second formula. So the second formula says NA plus NA complement equals the N universal set. And I think this should be pretty much straightforward to be true, because what you're essentially doing here is you're taking the total number of elements that belongs to A and the total number of elements that does not belong to A. So if you were to take everything that belongs to A and everything that does not belong to A, you're basically taking everything that there is. For example, if I say the universal set is 1, 2, 3, 4, and if I say A is 1 and 2, we know the rule of complement, it takes everything other than A. So it basically takes 3 and 4. So when you put A and A complement together, you clearly understand that it is the universal set. So the number of elements in A and number of elements in A complement should necessarily be the total number of elements in the universal set. But let's anyway go ahead and prove these two formulas in a more generalized and abstract manner, so that we can be sure of that these two formulas work for any given sets. So let's prove them. So we have this random set. I'm going to first try and prove the first formula. So let's say that this is the universal set and there is n1 number of elements that belong inside this section of A, and n2 number of elements that belong inside the middle section, and n3 amount of elements that belong inside this B only section. And let's call n4 here the number of elements that does not belong to A or B. Now remember this, when I say n1, n2, these are not the elements itself. These are the cardinality, meaning these are the number of elements that belong to that region. To be more clear, if I take an example to show you, 1, 2, 3, 4, 5, 6, 7, 8. So if you consider this example, 1, 2 and 4 in this example that I've given are individual elements that belong to that particular set. However, n1 is the number of elements there. So if I were to go ahead and show the numbers, this particular section of this example has 3 elements. This particular middle section only has 1 element. This particular section again has 3 elements. This particular section outside has 1 element. So these green numbers that I've marked on this example are the numbers that I'm trying to represent over here in this proof. So remember, these n1, n2, n3, n4 are not the elements themselves. These are the number of elements that are there in that given region. Now having said that, let's get into the proof. Let's start with the right hand side of the equation. Right hand side says NA plus NB minus NA intersection B. Now NA means number of elements in A. So total number of elements that belong inside the ring A is N1 plus N2. So NA, number of elements inside A, is the total number of elements here and the total number of elements here together, right? So that is N1 plus N2. And number of elements in B is N2 plus N3. That's N2 plus N3. And the common element is N2. So if you go ahead and do the math, N1 plus N2 plus N2 plus N3 minus N2, this plus N2 and this plus N2 will cancel off. So the final answer is N1 plus N2 plus N3. And we know that this is NA union B, because if you were to add N1, N2 and N3, you get all the elements inside the set A union B. So now that we've proved that this formula is generally true and it works for any given set of this nature. Now let's go ahead and try to do the same with the second formula. So we're going to do the same. We're going to take one side, which is the left hand side this time, NA plus NA complement. So we know number of elements inside A is N1 and N2. So N1 plus N2 plus, and the number of elements that are outside A are N3 and N4, because A complement literally means that everything except A. So that is going to be N3 and N4. And we can clearly see what are we doing here. We are adding everything there is within the rectangle. We are adding N1, N2, N3, N4. We are adding everything that belongs to the universal set. So this is N universal set. Everything that is there in the universal set. I hope these two formulas are clear for you guys now, and we'll be using these formulas a lot when it comes to solving word problems in Venn diagrams. But also in the next video we'll be looking into some direct questions just to make ourselves comfortable with these formulas. So if you're not that confident with the formulas yet, don't worry, I'll be covering my next video on this, where I'll be discussing more direct problems just to make yourself familiar with this formula. If you like my videos, show some support by clicking the like button, share it with your friends so that they can learn as well, and subscribe to get more similar math videos. Also, feel free to comment below if you have any doubts or if you want to suggest topics for my future videos. See you in the next video.